Hey, what's going on guys? Tanmay here. Welcome to my channel Simple Snippets, and let's continue with our M-way search tree topic that has been going on in the DSA course, in the DSA playlist. For those who have missed any of the previous videos in this DSA course, please check out this entire playlist. In the last video, we took an introduction to what is a M-way tree, what is a M-way search tree, how it is different from a binary tree. So in case if you have missed that, please do check that out. For those who've already watched that, let's continue with the topic, and today's title or today's topic is insertion and deletion process in a M-way search tree. So just like we have insertion and deletion in a regular binary tree or a binary search tree or an AVL tree, we have a insertion process, we have a deletion process in M-way trees as well, right? More specifically the M-way search tree. For those who need a quick recap, here's the first slide, which basically gives the definition of what is an M-way search tree and how it would look like programmatically. The structure of the M-way search tree is drawn. But just in simple terms, M-way search tree can have more than 2 keys, and M is the order in which the number of keys are there in one particular node. So if M is equal to 4, the number of keys, that is the number of actual values a particular node can hold, is going to be m-1, which is equal to 3. Okay, so this is something we've covered previously, so we're not going to go there a lot. But more importantly, as I said, in this video we're going to discuss insertion and deletion. Okay, alright. Before we start off with the insertion and deletion, one thing to note that is in a M-way search tree, just like a binary search tree, the smaller key values are generally stored in the left subtree of any particular key. Okay, so in this particular node n1, if you observe, the first value is 43 and all the values which are towards the left of 43, which means that for this particular key we have these two left and right pointers which are pointing to the left and right subtree for this particular key. Okay, so for this particular key 43, this is the left subtree or left pointer which is pointing to the left subtree, and this pointer is pointing to the right subtree. Okay, so this is left subtree entirely for this particular key, and this is the right subtree for again 43. Okay, similarly for 65 we have these two keys acting as left subtree, keys as in pointers, and this one is the right subtree for 65. So for 65 this is the left subtree, and all the values in this is going to be less than 65, and all the values in the right subtree, that is the pointer pointing to the right subtree, which is nothing but this whole thing, as well as everything towards its right? So even hash q2 is towards the right of 65, so all the values in this entire right subtree is going to be greater than 65. Similarly for 65, this is also coming to its left, so all the values over here are going to be less than 65. I know I did a lot of mess over here, but you get the idea, right? So this is something that you have to keep in mind, because this will come in handy when you are inserting as well as deleting. Okay, alright. Now let's start off with the first process, that is insertion process. Okay, so here we have a question which says create a M-way search tree of order m equals to 3 with the following key elements which are supposed to be inserted one by one, and these are the following elements that are supposed to be inserted. So elements as in keys. Okay, so elements and keys are one and the same thing. Okay, so what do we have over here? We have m equals to 3. So let's write m equals to 3. M equals to 3, which means that the number of keys in one single node is going to be m-1, which is going to be equal to 3 minus 1, which is going to be equal to 2. Okay, so keep this number in mind. Every node will have maximum 2 keys. Alright. So what is the process of insertion? So this is how you go about inserting in a M-way search tree. I have written few steps. So the first step is to insert keys in node till the count is m-1. So let's take this very first step and let's start off with the insertion. So let's say we have 14. So let's make our very first node. Let's call it n1. Okay, and let me just draw a box. Okay, so this is our first node n1. We know that it can hold 2 values maximum, right? So the first one is 14. So let's write 14. We'll start from left to right. Okay, whenever you're inserting values, we'll start from left to right, and depending upon which number is smaller or larger, that is how we will arrange these values later on. So right now 14 goes to the left hand side. Let's go ahead and look at the second number, which is 32. So let's fill up 32. We know that 32 is greater than 14, correct? So that's why it is coming to the right. In case we had 32 coming in first and then 14, what would have happened? We would have first inserted 32 over here, and when 14 came in, we would have shifted 32 over here and 14 would come in this place. Okay, so that's how it is done. Alright, let's move on. Now, the third number or third key value that we have to insert is 11. Now, this is where the second rule applies, which says if the node is full, that is number of keys in a particular node is equal to m minus 1, m is 2, number of keys inside this node is also equal to 2. So in that case, we have to insert this new key to the left subtree node where this key k new, that is this new key, is less than the parent key. Okay, so we are having to insert this 11. So 11 is supposed to be inserted. We compare it with 14 first and we determine that of course 11 is smaller than 14, and in that case we have to insert it in a node which is towards the left of n1, correct? So before that, remember that for this node n1, it can have m minus 1 keys and it can have m pointers which will point to 3 other or m other child nodes, right? So that's why this is called a m-way search tree, which means that one node can have m children. So for that we also need to create pointers. So let's do that. Okay, so I have created 3 pointers which currently don't have any value, but now we have to insert this 11, remember? And it has to be inserted towards the left subtree because 11 is smaller than 14. So for 14, we are talking about these 2 pointer values which are gonna act as left pointer and right pointer, okay? So we will create a new node. Let's create a new node first. We'll call it n2. And in this n2, we will insert this new key 11, which we are supposed to insert. So let's insert 11 over here. And now when you create this in the practical way, in the coding sense, right, in the computer, when you write program to create these data nodes in the memory, they will obviously have some addresses and we will use pointers to link to those addresses. So let's just assume there is some fictitious address which is pointed by this left pointer. Let's say the address is hash 16. So hash 16 will go over here, and that is how you link the second node with the first node. Okay, all right, makes sense. Let's go to the next number. We have 6. Okay, so 6 is again smaller than 14. It will go to the left, so we have to store 6 in n2. Now remember, n2 is still not full, right, because n2 can store 2 key values. Currently it has only 1, which is 11. So when you come over here and compare 6 with 14, of course 6 is smaller, then you go to the left hand side, and when you come to n2, when you want to store 6, you again compare it with the very first value and you realize that okay, 6 is smaller than 11. So now what you have to do is you have to shift 11 to the right and 6 will come at this place. So let's do that. So 6 comes over here and 11 is shifted over here. Okay, all right. Again, you don't have to add new pointers because we are not adding new nodes right now. We were just adding keys because one place was left out in node n2 so that we can fill it with a new key. Okay, all right. So 6 is also done. Let's move ahead to 7. So now again, 7 is smaller than 14. We will go to the left hand side of 14, which is we'll go to n2. Inside n2, we can observe that both of these places, that is the keys, are filled with key values. So of course node n2 cannot take one more element, which means that we have to create a new node. So let's create a new node. Alright, so now we've created a node n3 because we want to store 7 in it. So remember, 7 is greater than 6 but it is smaller than 11. So for 6, this one is the left pointer and this one is the right pointer. Both of them are currently blank. So for 7 being greater than 6, it has to go to the right side of 6, which means it has to go over here. And for 11, this is the left pointer. So since 7 is smaller than 11, it has to go in the left pointer, which means that the middle pointer is going to point to n3 now, correct? So that is how we have to link now. So this hash a is the address of this node created in the memory. So that's how you will do the linking. And this 7 will get stored inside this new node n3. Alright, so now that you've got a hang of it, let's quickly go ahead with all the other values. So we have 4. 4 is smaller than 14. We will go to the left of n1. We will go to the n2. 4 is again smaller than 6. So in this case, it will go to the left hand side of 6. Right now, towards the left hand side of 6, we don't have any other number, right? We don't have any other node. So again, we will have to create a new node. So let's do that. So 4 will come over here. Now remember, even though we had space in N3 to store one element, 4 is not meant to go to the right hand side of 6. So that is the reason we had to create one more node over here, right? Even though we had some space in N3. So 4 is done. Let's move. We have 3. So 3 is smaller than 14. Go to the left of 14. Inside these two nodes, we will compare 3 with 6. 3 is smaller than 6. So again, 3 has to go to the left of 6, which means 3 will go in N4 because N4 has a space. So 4 will be shifted over here and 3 will come over here, right? So 3 is done. Let's see the new number, which is 88. Now 88 is larger than 14. 88 is also larger than 32, which means that we have to create a node towards the right of 32. So let's do that. So 88 will come over here towards the right of 32, and this #2 will be stored as an address, and this is how the linking will be done, right? Then we have 93. 93 again goes to the right of 32, and 93 will come directly over here because we have space in N5. Then we have 54. So 54 is greater than 14, 54 is greater than 32, we will go to the left. But now N5, which is towards the left of N1, does not have any more space. We already have two elements. So now 54 will be compared with 88. 54 is smaller than 88. So we have to create a node which is left of N5. So let's do that. So we have N6 over here. Let's give it some random address. These are all fake addresses that we are giving, okay? So #17, and this is how the linking will be done. And inside N6, we will have 54, right? So then we have 37. 37 is greater than 32, so go to the right. 37 is smaller than 88, to go to the left. And 37 is smaller than 54, so 54 will be switched over here. 37 will be written over here in this same node. Then we have 21. So 21 is greater than 14 but smaller than 32, which means that 21 will be towards the right of 14 but towards the left of 32, which means that it will be in this middle pointer, right? So let's create a node over here in between, and 21 will be stored over here. Then we have 17. Again, 17 is greater than 14 but smaller than 32, so it goes over here, and 17 is smaller than 21, so 21 will be written over here, whereas 17 will come over here, right? Okay, so now we have 89. Alright, so 89 is of course greater than 32 in the very first node. Always we will start from the root node, from the top to bottom, when we are comparing these keys inside these nodes. So 89 is of course greater than 32. You'll go to the right of 32, which is N5. Inside this, 89 is larger than 88, but 89 is smaller than 93, which means that we will use a new node which will be pointed by this middle pointer, correct? So let's create a new node over here, and 89 will be stored over here. Then we have 62. 62 is obviously greater than 32, but it is smaller than 88. So from 32 we'll go to the right, from 88 we'll go to the left. Now inside this, 62 is greater than 37. 62 is also greater than 54, right? We are talking about this value and comparing it with 54. So if 62 is greater than 54, it will go to the right of 54, which means this address will be occupied. So let's create a new node first. So 62 will be stored over here. Then we also have 64. We'll store 64 over here itself because 64 is greater than 32. It is smaller than 88. It is again greater than both of these numbers, so it will go to the left, and 64 will come inside this node. Then we have 75. So 75 is greater than 32, but it is smaller than 88, right? So we'll go to the left. 75 is greater than both these numbers. We have to go to the right. So we'll come to the right hand side, which is N9. Inside this, of course, both the places, both the key values are filled. So we can't have one more element over here. So we'll have to create one more node. And since 75 is greater than both these numbers, we have to use the rightmost pointer. So we'll create one more node. Let's create it like this over here. I know we are having some space issues on the blackboard. Then we have 35 and 36. So 35 is greater than 32. We have to go to the right. But 35 is smaller than 88. We have to go to the left. 35 is also smaller than 37, which means we'll have to create a new node over here at the left of 37. So let's do that. and the last two numbers are gonna be stored over here itself, 35 and 36. Both of them are smaller than 37, right? So let's write them over here, and this basically completes our entire M-way search tree insertion process. And now we have this tree structure which is built on based on these different rules. The third rule I didn't say because it is exactly opposite to the second rule, because it is if the node is full and the key that is supposed to be inserted is greater than the parent key, you have to insert it to the right subtree. Okay, so and then you have to repeat this process. So these are the 4 steps. You can note them down, and based on this we followed and solved this one particular question. This was the whole insertion process. Now let's talk about deletion in this video itself, and we'll take this example itself so that we can get an understanding of both insertion and deletion in one single video. Now in deletion we have 4 different cases. So the very first case is deletion of a key with no subtrees. So let's say you want to delete this key, you want to delete this key, you want to delete this key, you want to delete this, or any of the keys which don't have further subtrees. Does this key 62 have any subtrees? No. But does this key 37 have any subtree? Yes, it has a left subtree. Remember, 37 has a left pointer #33 which is pointing to N11. So we are talking about case 1, which is deletion of a key with no subtree. So let's take very first example and we'll say delete the key k equals to 3. So in that case it is very simple, simply delete the key from the node. So this is the key value, you just find it in this tree. How do you find it? Of course you go by the rule, you have to compare, is 3 smaller than 14? Yes, so go to the left of 14, then you go to N2. Inside this we'll find for 3. Do we have 3? Are we finding any match? No. We'll compare it with the very first value. 3 is smaller than 6. Immediately go to the left of 6. We'll go to N4 and very first value is 3. Simply we have to erase it out. Alright, so this is case 1, very easy, when the keys does not have any subtrees. Now the case 2a and 2b are where we have to delete a key with either a left subtree or a right subtree. So let's take an example of when you want to delete 37. 37 does not have a right subtree but it has a left subtree. So let's take an example of case 2a and let's say now we want to delete key 37. So what happens in that case? So when you want to delete a key which has a left subtree, what you have to do is you have to replace the largest value from this left subtree with the value to be deleted. Okay, let me read it out again. We have to replace the largest value from the left subtree, from this left subtree. So when you want to delete 37, which is the left subtree, it is this node. Inside this we have to find out which is the largest value. Which is the largest value over here? It is 36. So you have to replace 36 with 37. That is what it is saying. Replace largest value from left subtree with the value to be deleted. Value to be deleted is 37. So you take 36 and put it over here, and then you have to delete the largest value from the left subtree, that is 36. Okay, so there is an indirect approach. Essentially when you want to delete 37, what you do is you take the largest value from the left subtree, substitute it in the place to be deleted. So essentially 37 got overwritten. So we achieved the goal of deleting 37. But since you have duplicate entries of 36, then you have to also delete this out. Now when doing this, the structure does not get changed, correct? Because now if you observe the rule where in the M-way search tree, for a particular key, the left hand side should always have smaller values, right? So for 36, the left side or the left subtree is N11. N11 has keys 35. So 35 is still smaller than 36, right? So this means that this M-way search tree property is still maintained. So let's take a case of case 2b and you'll understand it better. So in this case, we have to delete a key with right subtree. So in deleting the right subtree, let's say you want to delete 54. Okay, let's say you want to delete 54. 54 does not have a left subtree, but 54 has a right subtree, correct? What is the right subtree for 54? Let me mark it out. It is this entire hierarchy, right? This is the right subtree for 54. So when you want to delete 54, let's say you want to delete k equals to 54, what you do is you replace the smallest value from the right subtree with the value to be deleted. So in this entire subtree, which is the smallest value, 62. So 62 comes at 54's place. You replace 54 with 62. So basically 54 got deleted. But now you have two 62s, right? So we simply have to delete the 62 from its original place. Now in doing that, again the balance and the structure is still maintained. Not the balance, the structure. Which means that for the 62, this right subtree still has all the values which are greater than 62. Because that is the rule of M-way search tree. That is, for a particular key, the left subtree has smaller values and the right subtree has bigger values. Correct? Alright. Now the last case is where you want to delete a key with both left and right subtrees. So let's take an example of N1. Okay, node N1, and let's say you want to delete key 14. Now inside N1 we have 14. 14 has both an entire left subtree, which is this whole part, which is the LST for 14, and for 14 the right subtree is this part. Correct? Now in this case, when you want to delete a key with both left and right subtree, you can either replace the smallest value from the right subtree or largest value from the left subtree. You have an option with the key value to be deleted, and then you have to delete this replaced value. So if you were to check the largest value in the left subtree, in this left subtree, which is the largest value? It is 11. So you can either replace 14 with 11 and then erase this 11 out, and in doing so the M-way property is still maintained, because for 11 all the values to the left are still smaller than 11. Correct? 6, 4, 7 are still smaller than 11. So the property is still maintained. Or the other way to do it is you have to take the smallest value in the right subtree. So this small circle is the right subtree for 14. Which is the smallest value? It is 17. So you take 17 and you put it over here, and then you erase out 17. Now still the M-way search tree property is maintained, which means that for 17 the right hand side of 17 still has all values which are greater than 17. So 21 will be shifted over here, okay? But it is still towards the right of 17 and it is still greater than 17, and of course the left hand side values are still smaller than 17. So when you want to delete a key with both left and right subtree, you have two choices. You can either replace the smallest value from right subtree or replace the largest value from left subtree. So this is case 4, or basically case 3, because 2A and 2B are kind of the same cases. So this is the deletion process, and now you can experiment and go on deleting more values from this M-way search tree to get a little bit more practice and better understanding of the entire process. Alright, so this was the whole insertion and deletion process of M-way search tree. It is a little tricky if you don't practice it, so I would request you guys to take a pencil and paper and do the insertion. Insert multiple values in a M-way search tree. Take the M as a higher value. Over here we were taking M as equal to 3. You do it with a M-way search tree with M value as 4 or 5 to test yourself, to practice more. You do the insertion first and you then do deletion by taking all these different cases and practicing and getting the hang of it. Alright, so I'm gonna wrap up this video over here. I hope you understood the insertion and deletion process in a M-way search tree. In the next video we will understand more such concepts. If you are new on this channel and if you like this video, please give it a thumbs up and do subscribe so that you get notified whenever I upload similar videos. Thanks for watching. See you in the next one. Peace.